Hello guys, welcome back to another video of waves. Now we'll be looking at waves part 3. Waves part 3, we'll be covering transparency, which is about how transparent an object. So we'll be looking at transparent object, opaque objects, translucent objects. Also we'll be looking at refraction through lenses. Convex lens ray diagrams, concave lens ray diagrams, magnifying glass ray diagrams, and visible light. So one of our main themes is ray diagrams. Transparency. Transparent. A transparent object lets 100% of light rays straight through unchanged. We say the light rays have been transmitted through the object. So an example of this is a glass window. Translucent. A translucent object will transmit some of the light, but the light rays are changed in some way. Some of the light rays may be absorbed and or reflected. Because of this, it appears a bit different to a transparent object. It's a translucent object is like halfway between a transparent and an opaque object. An opaque object will not transmit any light at all. They will absorb and or reflect 100% of the light rays. They will seem like a dark black in color. Refraction in lenses. A lens forms an image by refracting light. The images formed by a lens can be upright or inverted, magnified or diminished, real or virtual. Many optical instruments use glass lenses to form an image. A lens forms an image by refracting light. There are two types of lenses: convex or converging lens, concave or diverging lens. And then here we can see, so for convex lens, it's just like a double arrow, and for a concave lens, it's a different symbol. So these symbols are how they're represented in a ray diagram. So on the top, we could see refraction by a concave lens and refraction by a converging lens. If you remember, we talked about concave lens and converging lenses in biology, where we looked at the nervous system. So this is how they determined which lens to use for what condition of the eye, myopia or hyperopia. Convex lens. Parallel light rays that enter the lens converge. They come together at a point called the principal focus. Principal focus is the point through which light rays parallel to the principal axis pass after refraction. So on the top we can see a convex lens ray diagram. So they're all coming towards one point. A convex lens can form an image on a distant object. The distance between the focus, basically the principal focus, and the lens is the focal length. The light can come through the lens in any direction and meet a singular point to form a real image. So a real image is one that can be projected onto a screen, unlike a virtual image, which is what happens when a concave lens, when light gets refracted through a concave lens. The real image is formed when light rays converge to a point can be projected on a screen. Type of image formed by convex lens depends on the lens used, distance from the object to the lens. So that's the ray diagrams. To draw a ray diagram, you have to draw a ray from the object to the lens that is parallel to the principal axis. So here on the image we can see the principal axis, and we can see the F, which is a focus point. Draw a ray which passes from the object through the center of the lens. So here, instead of drawing a proper convex lens, they showed the ray diagram way of showing a convex lens, which is a double-sided arrow. The ray diagram from an object placed more than two focal lengths away from a convex lens. Also, ray diagram on the bottom right, we can see a ray diagram for an object placed between 2F and F from a convex lens. So it's a difference in how the image is formed. So on the top one, it's real diminished inverted, and the bottom one, it's a bit underneath. And also key definition is that magnification is image height divided by object height. Magnifying glass. A magnifying glass is a convex lens used to make an object appear much larger than it is. So for this image on the left, the object is less than a focal length away. So the focal length, if we see from here, which we'll be learning about, the focal length of the lens is the distance between the lens and the principal focus. So the image is upright, magnified, and virtual. Concave lens ray diagram. Concave lenses always produce images that are upright, diminished, and virtual. So virtual meaning they cannot be projected onto a screen. Examples of these are door peepholes, where people look through a door hole to see if anyone's outside. The image will appear larger as it's further from the principal focus. Light. When light is reflected off a smooth surface, it goes in one direction, which is called specular reflection. We learn about this in waves part 1 and 2. So specular reflection, where it's a smooth surface, for example, like a glass door is smooth, which can be contrasted to like a rough surface like the road. If it reflects off it, it will scatter in all directions. Finally, we'll be looking at visible light. So shining white light through a triangle prism at a right angle can separate the different wavelengths, so that's how we see a rainbow. That's one way of seeing a rainbow. Within the visible light range of the EM spectrum, there's a spectrum of color. So the spectrum of color ranges from about 400 nanometers to about 7 times 10 to the minus 9. So that's 400 nanometers to 70 nanometers. Each color has its own frequency. So the 7 colors of the rainbow are red, orange, yellow, green, blue, indigo, and violet. When white light shines on an opaque object, some wavelengths of the colors are absorbed. These wavelengths are not detected by our eyes. Other wavelengths are reflected, and these are detected by our eyes. If an object appears a certain color, for example, grass, it appears green, it's because when white light is shined onto it, it absorbs all the other colors apart from green, which is what we see. A transparent object allows us to see clearly through it. Glass is transparent. Thank you for watching. Please like, subscribe, and look out for my other videos.